Okay, if we hear the word metal, we turn away. We don't want to learn it. We don't want to touch it. We don't want to know anything about it. Actually, I don't know the exact numbers, but I used to work in an agency where about like 5 of 40 of my iOS colleagues ever touched metal, ever even like worked with it, wrote like only five of them wrote a line of metal code. And I know I can't generalize these numbers for the entire iOS population, but I don't think the numbers will be any much different. And it's such a shame because metal lets us create things which are unique, fast, and extremely beautiful. And this may be a little bit subjective, but metal is also a ton of fun. And if you are in your 30s, you already run your first marathon and you are looking to do something in your free time, I recommend learning metal because it will take you another 2 years. So lots of time. This is my last meme in this presentation. Don't worry. But to this talk, basically, I will get you started with metal. I will try to explain like the basics. We will try to use metal in SwiftUI. And if some of the code during the end will look a little bit difficult, don't worry. It's just like to get the idea, and I will pass you all the code afterwards. So what is this metal which I'm talking about? Well, it's not a genre of music. It's something much more interesting. It's the low-level GPU programming framework for iOS, which got introduced 10 years ago in 2014 on the DubDub. And we use it for gaming, and scientific computing, video processing, basically everywhere you have tons of data and you need to process them very, very fast. It actually, in 2014, it replaced OpenGL, which was previously used. And why did actually Apple created something on its own? Well, back in the days, OpenGL had many issues. For example, OpenGL, the architecture was designed to work on CPU and GPU being on different chips. So because of that, when we wanted to pass the data from CPU to GPU, we would have to copy the whole data, and it would take a lot of time. But actually, Apple has the CPU and GPU on one chip, so it can actually just like pass the reference to the data, or for example, the shaders, which we will write, used to be built in the runtime, but with Metal, Apple let us build the shaders in the compile time. And there's many things which Apple did to make Metal work very better than OpenGL. And actually, OpenGL is underneath all of the things which we are currently using as iOS engineers, which is like UIKit, SwiftUI, SceneKit. So if you've worked with these technologies, you probably used Metal underneath. So why is it so difficult to write the Metal code? Why no one wants to touch it? Well, it's because to set up a basic Metal rendering pipeline, you are looking at least 100 lines of code. To show you how to visualize it, basically to render a simple rectangle on the screen, we would have to write a vertex and fragment shaders. So it means like vertex to define the positions of the rectangle, then fragment to define the colors. Then we would have to define our pipeline state, set it to the, in this case, render command encoder, pass it to the command buffer, and then through the queue, we would have to send it to the Metal device, basically to the GPU. And we would have to write, really, I wrote it myself, at least 100 lines of code to render a simple triangle. It's a lot of work, and a lot of things can go bad during this process. But luckily, from iOS 17, Apple introduced these 3 view modifiers called color effect, distortion effect, and layer effect, which simplify this rendering quite a lot. And this is what we will talk about today. As you can see, we are here passing an argument called shader. And what are shaders? Shaders are basically tiny functions that run on the GPU in parallel. But let me explain it on an example. Basically, if you have a texture which will have around like 10,000 pixels, normally to color this texture with some random color on CPU, you would probably write to 4 cycles, and then you would color basically the pixel one by one. But as we would color the pixels on GPU, we can do it by writing one function, which will be called at the same time for each of these pixels. So it's a little bit different than as we think about programming on CPU. On GPU, it's a little bit a mind shift, but let's get into it. So to see the code, basically to create our function on the GPU, which is called name, and it's called name, and it returns a color, which is written as a half-4, and we pass in 2 parameters. In this case, it's the position passed in as float2, and also the color passed as half-4, and any like custom arguments which we want, which are usually like any colors, images, or any other vectors, which might be like positions, frames, stuff like that. And then we also have to add this stitchable parameter so we can use this function in the SwiftUI context. And then on CPU, we just call this view modifier, in this case the color effect, and we reference the name, basically the name function, through the shader library, which is given by us by Apple. And if the name is right and all the arguments are in a correct order and in a correct name, it will be drawn and called like automatically. And as you could see, there's this like C++ based language which I'm using. It's called the metal shading language, and it's really based on C++. And for the scope of this talk, we will just need floats, float2s and half-4s. Float is normal float. Float2 is a vector of 2 floats. We will use that usually for any like positions, touches, frame sizes, stuff like that. And half-4 we will use, it's a vector of 4 halves, and we will use it to define a color. Then actual metal shading language has a lot of built-in functions. We will use some like normalizing functions, squaring, length, flooring, which is rounding down, and maximum function. And on a vector, we can perform any typical math operations, such as we can sum them, or basically any math operations we need. So the first effect which I will talk about is called the color effect. And as it works is that you pass in these 2 required arguments, which is the position of the current pixel and the current color of the current pixel. And you are supposed to return a new color for this like pixel, which we are currently working with. And then we can pass in some number of custom arguments, which we also need or want to determine the color. But the position and color is required in the header for the color effect to work. And it will be given to us, actually, we don't have to specify it on the CPU. It will be given to us on its own. So we call this view modifier. We will pass in the shader, and we can call it on some view. So let's try it on an example. We will write this like recolor shader, and what we will do, we will take this Cocoa Heads logo, which has a transparent background, and we will recolor all the non-transparent pixels with some like different color. And I can already tell you how are we gonna do it. If we just check the half-4, what it means, half-4 is a vector of 4 half values. We use it to define the color. Basically have the red, green, blue, and alpha values. So for red, we would use 1 as red, 0, 0 for green and blue, and again 1 for alpha, with 1 being the most prominent color and 0 the less, or like not prominent color at all. So to write our function on the GPU, we would call it recolor. It is returning HAL4 as a new color for the pixel. It's stitchable, so we can use it in the SwiftUI context. We are getting in 2 arguments, the float to the position and of the current pixel and the current color of the pixel which we are working in, which are the required for this color effect. And then we also need to pass in the new color, which is the color that we want to recolor it to. So what we can easily do in the current pixel, we can check if the current pixel's like alpha value is close, is 0 or close to 0, and if it's, which means that this pixel is probably transparent. And if this pixel is transparent, we just return the current color for the pixel. But if it's not, we know that this pixel probably has some color, and we will return like new color for this, and which will be the purple color in this example. Let me show you it quickly in code. Basically here we have this image, the logo, and at the end we are calling the color effect with 1 custom parameter, which is the purple color, but we can call it with like a different one. Let's use yellow. And if I run it, it will recolor the image to yellow. If I comment it out, you can see it's white without it. And if I mess up and put in like 2 more arguments, you can see that it does nothing because it didn't recognize this function on the GPU. So we actually have to really be quite clear and look out when we are working with this and defining it. So this was our recolor shader. So let's try to do something else with the color effect, because with the color effect, we also can do like filters on images very nicely. And here I'm just showing you the black and white shader. To get the gray value, basically, of the pixel, there's a thing that if the red, green, and blue are the same, then it means that basically the ending color will be in a shade of gray. And with this knowledge, we can define our black and white shader, which we will all again have to specify the position and the color, which goes in and returns a new color for the current pixel. And we can just calculate the luminance, basically the shade of gray, by averaging the red, green, and blue values of this color, and then just returning them as a new color. And if we run this on any image, it will make the image black and white. But we could also play around with the luminance, make it like more, make it less. It would affect the shade of gray, or create any other filters on images as which you can think about very easily. But with color effect, we don't only have to do any like effects, but we can also do any like custom drawing. Actually here, what you can see, it's not any like SwiftUI animation. It's a 3D, like it's a mathematical function which is visualized. There is a big purple circle in the screen center, and there's 1 small dot going around which we are moving by touch. Let me show that quickly in code. So we have this big purple dot in the screen center, and if we are going around, the 2 dots very nicely like blend in. So it's not a SwiftUI animation; it's just a function which is visualized. As you can see, as the parameters, we are passing in the touch location and also a frame size, which we are getting from the visual effect parameter. And we will just use the frame size to calculate, to normalize the screen, and the touch position to know where to position this small dot. So let's implement it. As I was showing you, we are passing in two custom parameters, the touch location and also the frame size. And this is actually the 3D function which we need to calculate somehow. And then if you look in the middle, about in like a z-axis 1 is there's like the red plane, which kind of reminds you of what you already saw previously. There is the circle, bigger circle in the middle, the smaller circle on the side, and they are like little bit blended together. And if we would see this on a 2D plane, this is the function. And if we look where the value is 1, we can see that if we draw everything that's under 1, we can draw it with purple. And if we draw everything which is like above 1, we can draw it black, which would actually give us the shape which we are looking for. And we are also, as I said, we are passing in the frame size for normalization, because every like position here is in the like user coordinates system, which means that even the touch, even the position which we are defaultly getting has to be normalized first, so we can like easily create the mathematical function from it. So let's start by creating the big dot in the screen center. We are just getting the screen center by dividing the frame size by 2. And then we are checking what's the like position of what's like the direction from the current pixel to the screen center. We are normalizing it, and then we are basically getting the circle by calling the length function upon it, and we are just multiplying it by 10 to make it smaller. But if I would now like just draw out the C distance, I would just get and I would check like where the C distance is like smaller than 1, and I would draw purple there. It would give me a purple dot in the screen center, and if I would color all the pixels black, I would basically get just a purple dot in the screen center. Yes, this one. Okay, what we are missing is this second dot, which is in the space, in the user's touch location. And we can kind of get it the same way, but we just subtract the touch from the end position to center. So we kind of like move the second dot away from the screen center, and we are just multiplying it by 20 to make it look a little bit smaller than the screen center dot. And now, if we want to do like the actual blending of these two dots, I'm using this, like I'm basically squaring the C distance, and then I'm multiplying it by the touch distance. But you could probably use like any other function which you can create out of these like two parameters. This one works really okay for me. So this will kind of blend these two together and give me this 3D function which we are drawing. This is the distance in code. And now we have the 3D function created. So as I was mentioning at the start, we will just check where the z-axis, or basically where the function is smaller than 1, then where in this position we will draw the purple color, and if it's like bigger than 1, we will draw black. So I'm just checking if the distance is less or equal 1, I'm returning the purple, otherwise I'm returning black. And that's how we get this like interactive dots shader. But we can really play around with it and create like anything you really want. And it's not that hard as you would think in the first place. So, but that's not everything. What we can actually create with these color effects are any type of like textures, which you can put in a background. There's a guy that is speaking tomorrow, and in his app, he's actually using the color effect to draw a texture in the background of his app. He's called Hidi. I promised him that I will mention his name, but I won't show you, I won't code the texture shader with you here because it's kind of complicated. Here you can see how it looks like. Yeah, so you can also have some more complicated texture shaders. And I was playing around and did some like loading animations, which I don't know how would you do that easily in SwiftUI, but there are like few lines of code in Metal. So you can do like many different like loading animations, and basically you can draw anything you want with the color effect. So this was the color effect, but we also have two more to go. So the second one is called the distortion effect. And how it works is a little bit different, like compared to the color effect, because here, as you can see on the input, you are getting only the position of the current pixel, but not the current color anymore. And you are not returning a color, but you are supposed to return a position. So what it does is that with this like shader, you are returning a position where the new pixel should be like sampled from the current texture. So it's a little bit different from the color effect because we can't really specify a new custom color. We can only sample from the current context. But it's used to create some very cool things, usually any like type of distortions, transitions. I'm here using it to create some pixelation. We will see it in a minute. But if we check the SwiftUI view modifier, we can see we are adding one more parameter, which is the max sample offset. And it's the maximum distance in each axis between the return source pixel and the destination pixel position. But I will visualize it for you. Basically, if we are moving this animation, we are returning the position X and position Y, but we are adding some time to it, which we are slowly like, animating. So the texture is kind of moving. So if the max sample offset is 0, the texture gets cut out of the screen. But if we are also animating or moving the max sample offset, it is not like cropped anymore. So if the texture looks bad for you, just play around with the max sample offset, long story short. But let's create this pixelate shader. It's a shader which pixelates the texture like over time. So to do a pixelation, basically a texture is made up of many pixels. And to pixelate texture, it basically means to divide the texture into like small groups, and then each group will take in a color. Basically, what we are doing, we are dividing the texture into small groups, and then in each group, we are checking the top left corner, sampling the color from the top left corner of the group, and then we are passing the one color for the whole group, which kind of creates the pixelation. So in code, we are passing in the position, which is required for this distortion effect, and also the strength, which is in how many groups we want to divide the texture. So like how much should the image be pixelated, and we are returning the new position where the new color should be sampled from. And we can do it very easily by, we are dividing it by the strength for the number of groups and also multiplying it. But when we divide it, we floor it, which means we round it down, which we can move the sampling to the top left corner of the group. And when we multiply it back, the new position is a little bit shifted. So as was showing on this image, now we are sampling the top left corner of each group. And we can just return the new coordinates as a place where it should be sampled. And if we just increase the strength over time, it will do this pixelation animation. And the third one is called the layer effect, which kind of solves the issues which we had with the color and distortion effect, because the color effect is really cool to do any like drawings, but it can't really access its surroundings as with the distortion effect, because we kind of don't know what is around. But then the distortion effect couldn't return any like new color. And then that's really cool that we have this layer effect, which is less efficient, but how it works is that on the input, we don't have a color, but we have a layer. So we get the whole layer and we are returning a new color. So we can kind of check what other pixels are in the texture and make our decision about the final color based on that. What's the layer? We have to include it by adding this SwiftUI header. And the layer struct just inside have a 2D texture and the sampling method. So if we call this sample method on our layer with some position which we want to sample, it will return us the color which is on this position. And as we also use the max sample offset as we did in the distortion effect. And what I will show you is this wave shader, which is this like circulating wave animation going from your like touch position. Basically, if you touch the texture in some place, it will create like this wave, basically a donut, a distortion in a donut that's enlarging over time. But this could actually be very easily created with the distortion effect. So that's why we also color the distortion. We added a color. So now the distortion animation is orange. Let's see it in the code. If I like tap on the header, for example, it will create this like circle animation with the distortion. Let's go over the parameters. We are passing it some width, which says how wide the donut should be. So now if I click here, the animation will be very much like the donut will be like so much wider. It's kind of similar to the default Apple animation which you get when you connect two iPhones together. Then we have the amount parameter, which says how like the strength of the distortion. So here the distortion is very strong. And we are passing in the color. So if we change it to, let's say, blue, and we run it, we will see that now the animation is blue. And we are getting the time from this timeline view. So the wave shader. So the first thing which we need to do is create the distortion, which we will then apply to the donut itself. And let's start just like with a simple distortion from the screen center. As you can see, we are passing in the position, the layer. the frame size just to normalize things, and also the spread, which in this case we will just animate the spread over time to make the distortion animation like moving. We are getting here normalized position, normalized screen center position, and we are just checking what's the direction of our current pixel to the center. And then we are calculating like the displacement, which we are then sampling from the layer, and we are multiplying it by the spread, so we know like how much we want to actually distort the texture. The second step would be to make the distortion just from the touch location, which we can easily do just by removing the screen center and adding a touch position. And everywhere where it was like a screen center, we will add a touch. And basically with this, we already moved the distortion to the touch location, which was nice. But then the distortion was like everywhere on the texture. So we have to limit it somehow. And actually, if we limit it from the outside and from the inside, and leave just the distortion of the donut shape, and then apply this on the texture, we can get the final animation. So let's start with just limiting the outer distortion. To do this, we will need this smooth step function, which is a function used in computer graphic. And basically how it works is that you pass in two edges, edge 0, edge 1, and some value. And if the value is lesser or equal than the first edge, it will return 0. If it's bigger or equal than the second edge, it will return 1. And for all the values in the middle, it will like smooth them. It will use the Hermit interpolation and smooth them out. So we are creating basically this map. Here, like everything what we will be black will still be distorted, but all the white places won't be. So to do this, we can just call the smooth step. And we know that we want to smooth it out from the spread minus width, which is like the length, how wide the donut should be to the spread. And we pass in the length of the direction to the touch. And if we draw it out, if we draw out this map, we get this animation. Here it is in a code. And then we also need to limit the inner distortion. And we can do it kind of the same, also using the smooth step function. To limit inside, we have to remove the width 2 times, and then we are not, I think it's the. And if we multiply the inner and outer map, we will get this donut shape, which, if we see the whole code, if we draw out the distortions just in the places where the donut shape was, where we had the black pixels, it will create the final animation. And to add the tint, we just need one more custom parameter, the tint. And what we can do is just again multiply the map, which was the donut shape, by the tint, and we will just add it to the final color. So it will create the final donut animation, this one. So my final thoughts, just to summarize this out, what we got these 3 view modifiers that are available from iOS 17. The first one was the color effect, which we can do to do any like filters and effects on textures and images, but we can also do any like custom drawing with it. Then we got the distortion effect, which we use to do any like distortion, transitions. I saw it used even on like transitions between view controllers if you want to see something, like create something custom. And then we got the layer effect with what we can do basically everything. It also has some limitations. The first one and the biggest one would be, of course, we can use it only on SwiftUI views, which means if there is like UI kit view underneath, we won't be able to use these view modifiers. And what Apple does, it creates a placeholder warning image instead, the solution. Then only one image parameter can be passed to a shader. So basically, if you want to pass some like custom parameters, one of them can be like image, a texture, and we can pass only one currently. Third limitation would be that when you write like normal metal code, Xcode actually has pretty good built-in debugger. But this debugger does not support the stitchable functions. Stitchable was the parameter which we have to use at the start of our GPU function, which will be used in SwiftUI. So we can't really currently use the metal debugger to debug these metal shaders. I found out that if I wrote the like very, very complex shaders, I saw some like lower performance, which I would probably not get in if I would set up the metal in UIKit like on its own. So it's like a little bit laggy with more complex shaders, but the ones which I was showing you in this presentation work fastly. And the final limitation would basically be that you don't have any additional control over the metal shaders than what I basically showed you in this presentation. So you can't really specify like anything else. And in metal, you can specify everything, like the pixel format, complete everything. But here, there is like no additional control, at least currently. So to sum it up, what would I use SwiftUI modifiers for versus where it's really needed the manual setup? I think the SwiftUI modifiers are really cool if you need some like effect on an image, as I showed you, or to draw something custom, do the transition between views. But if you are actually doing any like heavy work, you need to, for example, even like save the frames at the end somewhere. You are not gonna get them from SwiftUI, at least as far as I know. You are not able, of course, to draw anything like very, very heavy. You would not use this to create a game. So for all of these like more difficult situation, you would still have to set up metal, let's say, manually inside UIKit. So the next steps, if you want to learn a little bit more about metal, I would recommend the Metal by Tutorials, which is a book from Codeco, or the Metal Programming Guide by Jenny Clayton. There's also a link to the metal documentation. Paul Hudson wrote a library of some shaders, which can be used currently in SwiftUI. And a shader toy is a big library of any shaders for OpenGL, but they can be easily rewritten for to metal shading language, so you can use them with SwiftUI. So you can also check shader toy if you need some like inspiration. That would be everything from my talk. Here you can see the GitHub repository with the presentation and all the links. And you can find me on LinkedIn, Instagram, and X. And thank you for your time.